This video is going to cover the fundamental theorem of algebra, as well as finding zeros of polynomials. I am going to start by giving you the fundamental theorem of algebra. It says every polynomial of degree n has at least one zero in the complex set of numbers. This is saying that if you set any polynomial equal to 0 and you try to solve, you will get at least one solution, but that solution might be an imaginary number. It might be a real number. The second part says every polynomial of degree n can be written as a product of n linear factors. So if you have a fourth degree polynomial, something with an x to the fourth, you will get 4 linear factors. And your factors are always going to be of the form x minus c, x minus c2, x minus c, etc., where c1, c2, etc. are complex numbers. And these factors are always going to be related to the zeros of your polynomial. If x equals c is a 0, then x minus c is a factor. So these factors are all of the form x minus the zeros. Let's see how this works by doing an example. Find all zeros of the polynomial f of x equals x to the fourth minus 8x squared minus 9. Then write as a product of linear factors. This is a fourth degree polynomial, so our final answer should have 4 linear factors. So first thing I'm going to do is set this equal to 0 and try to solve. I think we can actually factor this one. This is one of those quadratic type equations. I have 3 terms, and if I let u equal the x squared right there in the middle, if u is x squared, then u squared would be x squared squared, or x to the fourth. So that means we can replace this x to the fourth with a u squared. The x squared is u, and now I have a quadratic equation in terms of u. So I have the equation u squared minus 8u minus 9 equals 0. This is something we can factor. 2 numbers that have a product of 9 would be 9 and 1, and if I do negative 9 and positive 1, that does add up to that negative 8 in the middle. So that means u minus 9 could equal 0, or u plus 1 could equal 0. Solving for u, I get u equal 9, or u is negative 1. But we're not solving for u, we're trying to solve for x, and so we started this problem by saying u was x squared, so I'm going to replace those u's with x squared. So now I've got x squared equals 9, x squared equals negative 1. I can solve for x by taking the square root. Don't forget the plus or minus. So x is plus or minus root 9, or x is plus or minus root negative 1. Square root of 9 is 3, and square root of negative 1 is that imaginary unit I. So my zeros are positive 3, negative 3, and positive I and negative I. I have 2 real zeros and 2 imaginary zeros. This polynomial can be written as 4 linear factors, and each factor is going to be of the form x minus 0. So I have a factor of x minus 3, x minus negative 3, x minus I, and x minus negative I. I'll write that as x minus 3, x plus 3, x minus I, x plus I. So fourth degree polynomial has 4 factors. Some of those factors just happen to have imaginary numbers in them. All right, if our polynomial has real coefficients, which the polynomials we're going to look at in this class will have real coefficients, then complex zeros have to occur in conjugate pairs. And in my previous example, notice that we had 2 imaginary zeros, positive I and negative I. Those imaginary zeros are going to occur in pairs, and they're going to occur in conjugate pairs. So to explain what I mean by that, I'm going to do an example. We are going to find a polynomial with real coefficients that has zeros at x equal 2 and x equal 2 minus 3i. So we have a 0 at x equal 2. Because x equal 2 minus 3i is a 0, x equal 2 plus 3i is also a 0. 2 minus 3i and 2 plus 3i are conjugates. Conjugates are of the form a plus bi and a minus bi. So all I did was I changed the sign between the real and the imaginary part. So my polynomial has to be of the form x minus each of the zeros. So x minus 2, x minus the quantity 2 minus 3i, x minus the quantity 2 plus 3i. Or if I distribute those negatives, x minus 2 plus 3i, x minus 2 minus 3i. Now we can multiply this out and verify this is a polynomial where all the coefficients are real. When we multiply this out, the I should disappear. So I'm going to start by multiplying the more complicated pieces. I want to multiply x minus 2 plus 3i and x minus 2 minus 3i. I could go ahead and distribute the x to all three pieces in the second parentheses, then distribute the negative 2, then distribute the 3i, combine like terms, and simplify. But I do have a little bit of a shortcut here. I noticed that the first parentheses I'm looking at is x minus 2 plus 3i. And the second set of parentheses is an x minus 2 minus 3i. I have something of the form a plus b times a minus b, where a is the x minus 2 and b would be the 3i. The only thing different in these two parentheses is the sign between those quantities. And anytime I multiply a plus bi and a minus bi, I'm going to get that difference of squares pattern, a squared minus b squared. So that means when I multiply these two quantities, I should get the first piece, the x minus 2 quantity squared, minus the second piece, the 3i squared. X minus 2 squared is x squared minus 4x plus 4. Recall you have to actually FOIL that out if you don't remember the pattern. X minus 2 times x minus 2 gives us the x squared minus 4x plus 4. 3i squared becomes 9i squared. Since I squared is negative 1, I can replace that with a plus 9. Combining like terms, we get x squared minus 4x plus 13. Finally, we haven't divided by this x minus 2 yet, so I'm going to take x squared minus 4x plus 13 and multiply that by x minus 2. Start by distributing the negative 2. Negative 2 times positive 13 is negative 26. Negative 2 times negative 4x is positive 8x. Negative 2 times x squared, negative 2x squared. Now I'm going to distribute the x. X times 13 is 13x. X times minus 4x is minus 4x squared. X times x squared is x to the third. Combining like terms, we get x to the third minus 6x squared plus 21x minus 26. And that's my solution. This polynomial has all real coefficients. After we did the multiplication, there are no i's left in the problem. And it has zeros at 2, and at 2 plus 3i, and 2 minus 3i. Let's take a look at another example. Given that x equal 1 is a zero of the polynomial, find all other complex zeros. Then write as a product of linear factors. So in this problem, they're telling me what one of the zeros are. I know that x equal 1 is a 0. So if x equal 1 is a 0, then x minus 1 has to be a factor. I can't factor this polynomial using any of the techniques that we reviewed at the beginning of the semester. I can't factor by grouping. That's not going to work. The numbers just don't work out if we try to factor by grouping. But because we know x minus 1 is one of the factors, we can actually use division. We can take this polynomial and divide it by x minus 1. I'm going to use synthetic division to do that. If I want to divide by x minus 1, I'm going to put a plus 1 outside of my box. Then I'm going to fill in the coefficients of my polynomial. 1x to the third minus 2x squared minus 5x plus 6. Bring down the 1, 1 times 1 is 1. Add, I get negative 1. Negative 1 times 1 is negative 1. Add, we get negative 6. Finally, negative 6 times 1 is negative 6. I add, and I get 0. And I should get 0. If x equal 1 is a 0, and x minus 1 is a factor, when I do the division, there should be no remainder. And so now I know I can factor the x minus 1 out, or divide it out, and I am left with 1x squared minus 1x minus 6. I got those coefficients of my quadratic here by looking at my answer from my synthetic division. And now I can actually finish the factoring. X squared minus x minus 6 is something we can factor. 6 is 3 times 2, and if we do a negative 3 and a positive 2, that does add up to give us the negative 1 for the middle term. So my polynomial is factored now. Notice I have a third degree polynomial, and I have 3 linear factors. So we're actually done with the factoring part. This polynomial is written as a product of linear factors, and my zeros are x equal 1, x equal 3, and x equal negative 2. I got those zeros by looking at my factors, setting them to 0, and solving. My next example says the graph of p of x equal x to the third minus 7x squared plus 8x plus 4 is shown. Use the graph to find all zeros. Then write as a product of linear factors. So this problem is similar to the previous problem, but this time they're not telling us what one of the zeros is. However, since they gave us a graph, we should be able to identify some of the zeros from the graph. And when I look at this graph, I can tell that there is a 0 somewhere between 0 and negative 1, but I can't see exactly where that value is. And there is another one that's a little bit bigger than 5, but again, I can't really tell what that value is. However, right at x equal 2, there is a 0. So x equal 2 is a 0. That means x minus 2 has to be a factor. And so now I'm going to use the same process that I did in the previous problem. I'm going to divide the x minus 2 out of this polynomial by using synthetic division. To divide by x minus 2, I put positive 2 outside of this box, and then I write down the coefficients of my polynomial. 1x to the third minus 7x squared plus 8x plus 4. We bring down the 1. 1 times 2 is 2. Minus 7 plus 2 is minus 5. Minus 5 times 2 is minus 10. 8 minus 10 is negative 2. And then finally, negative 2 times 2 is negative 4. We add and we get 0. If I hadn't gotten 0, that means I made a mistake, or maybe I read the graph incorrectly. So I'm glad that I got a remainder of 0. That confirms that we were right. X equal 2 is a 0. And so those numbers at the bottom, the result of my synthetic division, tell me what I'm left with when I factor out or divide out the x minus 2. We are left with a 1x squared minus 5x minus 2. Now, the quadratic that we're left with, x squared minus 5x minus 2, unlike in the previous example, this can't be factored. I can't think of two numbers that have a product of 2, but a sum of negative 5. So instead, we can solve this quadratic, we can find our other zeros by using our quadratic formula. So we'll let a equal 1, b equal negative 5, and c equal negative 2. The quadratic formula says we take negative b, so negative negative 5, plus or minus the square root of b squared. That would be negative 5 squared minus 4 times a times c, 4 times 1 times negative 2, and then all over 2 times a, or 2 times 1. Simplifying this expression, I get positive 5 plus or minus 25. And then that minus a minus becomes a plus, so plus 8 all over 2. That would be 5 plus or minus root 33 divided by 2. So this polynomial has 3 real zeros, and I can actually see them in the graph. The graph has 3 x-intercepts. One of them is at x equal 2, another at 5 plus root 33 over 2, and the last one at 5 minus root 33 over 2. So those are my zeros. So that means I can actually write this polynomial as x minus 2 times x minus the quantity 5 plus root 33 over 2 times x minus the quantity 5 minus root 33 over 2. So notice that each of the factors is x minus a 0. I have one more example to show you. Let's use the fact that x equal 3i is a 0 of the polynomial p of x equals x to the 4th plus 2x to the 3rd plus 14x squared plus 18x plus 45 to find all zeros. So this problem is similar to what we've done before, except they're giving us an imaginary 0, 3i. And those imaginary zeros always come in conjugate pairs. So that means x equal negative 3i is also a 0. So I'm going to start this problem just like the previous problems. It's going to be a little bit uglier, but I'm going to do the same thing. If x equal 3i is a 0, then x minus 3i is a factor. So I'm going to use synthetic division to divide x minus 3i out. So I drew my box, I put the coefficients of the polynomial in there, and I have that 3i written to the left. Bring down the 1, and then we multiply. 1 times 3i is 3i. I add, and I get 2 plus 3i. Now we multiply. 2 plus 3i times 3i. I'm going to distribute. That gives me 6i plus 9i squared. I squared is negative 1, so that's 6i minus 9. I'm going to take the 6i minus 9, put it up here, and we add. Now, we can only add the real parts, so 14 minus 9 is 5, and this becomes 6i plus 5. I multiply again. 6i plus 5 times 3i. I'm going to distribute. 3i times 6i is 18i squared. 3i times 5 is 15i. I squared is negative 1, so this becomes negative 18 plus 15i. So I'll write that in here, and when we add, the 18s go away, and we're just left with 15i. All right, one more. 15i times 3i would be 45i squared. I squared is negative 1, so that's negative 45. We add, and we get 0. I'm glad we got 0. If we didn't, it means I made a mistake. Now, our answer is actually really ugly, but we also know that x equal negative 3i is a 0. We know these complex zeros come in conjugate pairs. So I'm going to take my result, which is really ugly, and I'm going to divide again. This time, I'm dividing by x plus 3i. So I'm going to write the negative 3i outside of my box. And when I do this division, because I took the conjugate, things should simplify down really nicely. I should actually get rid of all the i's. So bring down the 1. 1 times minus 3i is minus 3i. When I add, those 3i's go away, and I'm just left with 2. 2 times minus 3i is minus 6i. I add. The 6i's go away. I'm left with 5. 5 times minus 3i is minus 15. We add, and we get 0. And that's good that we got a remainder of 0. That means we were right. The negative 3i, the conjugate, is also a 0. So at this stage right now, we have factored or divided out x minus 3i, and then we divided out x plus 3i. After dividing both of those things out, we are left with 1x squared plus 2x plus 5. And that remaining quadratic is something that I can work with. We can set that equal to 0 and try to solve to find the other zeros. X squared plus 2x plus 5 equals 0. I'm going to have to use a quadratic formula on that. So we'll take negative b plus or minus the square root of b squared minus 4ac all over 2a. That becomes negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2 times 1. Or negative 2 plus or minus square root of 4 minus 20 all over 2. And let's see, I think we can simplify this further. 4 minus 20 is negative 16. And the square root of negative 16 is 4i. Now I have a common factor. Everything is divisible by 2. Negative 2 divided by 2 is negative 1. And 4i divided by 2 is 2i. So when I solve the quadratic equation, x squared plus 2x plus 5 equals 0, I get x equal negative 1 plus or minus 2i. So this polynomial actually has 4 imaginary zeros. Positive 3i, negative 3i, negative 1 plus 2i, negative 1 minus 2i. It is a 4th degree polynomial, so we should be able to write it as 4 linear factors. Each of our factors would be x minus one of these zeros. Let's see, they did not ask us to factor it, so this is my answer. I do want to show you if we actually graph this polynomial, it doesn't have any x-intercepts. It doesn't cross the x-axis at all. And that is because all of these zeros are imaginary. That's why we're not seeing them in our graph. All right, that was my last example. Please let me know if anything in this video is unclear.